Hello everyone, I am Vijay Anand. Our rating for the TARP project is Accelerated Modeling and Testing of SOFC aided by A. First, I going to give introduction about this project. Solid oxide fuel cells are emerging as a promising technology in electrochemical energy production system. Due to their high efficiency, fuel flexibility and option for integration into chip system, a SOFC cell usually contain a thick layer of ceramic electrolyte held between porous electrodes. The porous cathode allows diffusion of oxygen from air into the cathode electrolyte interface where they react with free electron in the cathode to form oxygen ions. These ions are transported through the electrolyte where they react with oxidized fuel that had diffused through the anode. This leads to release of electron which flow to the external circuit to establish electrical energy. The performance of the cell is heavily dependent on the operating condition and the material of construction. In this work, we will be discussing and studying the impact of various physical parameters like temperature, inlet mass, flow rate, and composition of fuel and air on performance of the cell. Though there is a lot of published work that the study of the impact of such parameter on the performance of nearly all of them are based on either an experimental or numerical approach. We will be studying the impact of this parameter using a data-driven approach by building machine learning model. We will also be comparing and validating the result obtained from the ML model with a CFD model.
Neural networks. Neural networks is divided into three parts: feed forward, back propagation, and updating the weights. All the three are represented in a form of algebraic equations for a single neuron. This algebraic equation for the multiple neurons is simplified and represented in the form of matrix. Feed forward. Feed forward is the process of feeding the information through the value of the neural network. The information which are passed into the layer are assigned a weight. Back propagation. Back propagation is used to reduce the error in predicting the outcome from the neuron. Error is the difference between the written value and the expected value. After calculating the error, it is passed on the lower level and it corrects the error by splitting the error. In splitting the error, it cannot be split evenly between the input due to the difference in their weight for each input. Updating the weights. Weights are updated such that the error function is minimum or global minimum of the error function. Procedure carried out to perform ML. Data collected from the plot digitalization is imported and cleaned to remove any rows with missing values. The clean data is split into training and validation set, and the training set is visualized to perform any abnormal and extreme values. Then the training data set is normalized to ensure there aren't extremes that will distort the results from training. A neural network is created with 5 above mentioned input layers: hydrogen flow rate to anode, oxygen nitrogen flow rate in cathode, stack temperature and cell voltage, and 2 hidden layers with 10 and 7 neurons respectively, and one final output neuron. Current density. The model is then tested with the validation set. The model assessed with the validation loss to check the performance of the model. The validation loss needs to go down with each epoch to ensure that the model is working well. The final results from the model are evaluated in the form of mean absolute error.
A cross-flow planar SOFC with multiple air and fuel channel is designed in Fusion 360 and exported as step file and assembled in ANSYS design modular. To prevent divergence, ANSYS workbench meshing is used, which creates a highly structured mesh of high-quality orthogonal elements. The mesh generated has an average element size of 2 into 10 power minus 6 meter and 12,68,560 elements. Fluence fuel cell and electrolysis module is enabled. The SOFC model is selected, allowing the equations to be enabled. For the model, the boundary conditions and material properties are selected according to the table provided. The convergence residual are set at 10 power minus 3 for continuity, velocity species, electric and protonic potentials, and 10 power minus 6 for energy. To obtain good initial values, a hybrid initialization of 10 iterations is performed. The solver continues to run until the set residual is reached and convergence is achieved. To obtain the desired results, the model is post-processed.
Now we are going to validate our machine learning and CFD model. To validate our machine learning model, training data set is fed to this algorithm. Training data sets include flow rates and temperature and voltage. Then the algorithm generates the output as current density. This predicted value is then compared with the actual current density from the literature. Then this is used to calculate the mean absolute error. The mean absolute error is used as a parameter to check how accurate our model is. The lesser the value, the more accurate. For our machine learning model, we were able to predict the current density with the mean absolute error of 0.019318. This accuracy is demonstrated in the figure. To validate our CFD model, the polarization plot for our simulation is validated against the polarization plot available in the literature. The error between the simulator and the standard literature is used to find how accurate our CFD model is. This has been demonstrated in the figure 2. Conclusion. We have successfully implemented our machine learning and CFD model for our SOFC system. It has been observed that the machine learning model takes less time compared to the CFD model in predicting the current density. This can be further improved by training the machine learning with a large data set, and this can be used to predict the various parameters more accurately and quickly. Thank you.